Hello everyone and welcome to another session of Abacus tutorial. In this session we are going to simulate deep drawing process, which is great for producing parts that contain large depths. As you can see, the simulation contains of four parts: die, blank holder and the punch. The blank sits on die and blank holder by exerting force prevents the blank from moving or rotating in any direction. Then punch comes in and uh, pushes the blank deep inside the die, and the desired material or the desired product is uh, obtained. This is the result of our simulation. As you can see, the blank has deformed with the force of the punch, and the sides of the blank have wrinkles. This is because of the blank holders force was not enough. We have simulated the process like this to show you the wrinkles that can occur. By adding the force of the blank holder, we can remove these wrinkles. One other important thing in this simulation is an isotropy. Metal sheets that are used in shaping processes have some anisotropy, meaning that the blank's mechanical behavior or properties along different directions are different. This gets important for processes like deep drawing, and the blank's behavior must be investigated. Here we have considered anisotropy in the simulation too. Next, you can see the dimensions of the parts that we are going to create. These dimensions are in meters. Okay, let's go to Abacus and create the first part. The first part to create is the die. So here are the dimensions. Our die is a 3D discrete rigid shell, and the type is SWIP. The approximate size is 0.5. First, we should create the SWIP pass. Adding fillet with the radius of 0.05 or 5 centimeters. Next is the sketch, but first we should enter the maximum scale equal to 0.3. This is the shape of our sketch. which is going to be like an inverted L shape. Okay, this is the die, but we should add fillet to these edges, and the size of our fillet is equal to 0.01. And at last, assigning a reference point to this discrete rigid body. Next part is the punch to create. Punch is a 3D discrete rigid solid extrusion body with the approximate size of 0.5. The punch is a square that has a fillet on one edge or on one vertex with the radius of 0.05. The equivalent depth is going to be 0.2, and last we must add fillet to these edges. 0.005. Okay, next, creating shell from solid and assigning a reference point to this part. The third part is the holder, the blank holder, which the dimensions are here. The blank holder is a 3D discrete rigid shell with the technique of sweep. First, we should sketch the sweep pass, which according to the dimensions must be like this. Adding fillet. These two sides are equal. 0.1. Next, the maximum scale for the sketch is 0.3, and the sketch is going to be like an L shape. .095 and 0.095. We add a fillet in this place with the radius of 0.005. Okay, this is the blank holder. Next is our blank itself. So the blank is going to be a 3D, first let me sign it, a 3D deformable solid, shell planar, and the approximate size is going to be 0.5. The blank is a square again, with the sides, let me, the sides equal to 0.25. Okay, next we should define our properties. Here are the properties you can see, and if you want you can pause here and add this property to your model if you are simulating with us. So next we go to property module and create a new material. First let me define my dimensions. Mass in kilograms, length in meters, and density so is in kilogram per cubic meters, and stress or pressure dimension is going to be in Newton per square meters, or pascals. Okay, so density is equal to 7,850 kilogram per cubic meters. Young modulus is 210 gigapascals, and the Poisson ratio is equal to 0.35. Next, we should define the plastic yield stress and strain. Okay, plastic strain is defined. Next, we are going to define an anisotropy using Hill's potential function. So we go to the sub option and potential. Here we add data like this. 2 1 or 3 1 1 and R23 is 1. Okay, anisotropy is defined. Next, we should create a section for our blank. So the section is shell homogeneous, and the shell thickness is equal to 1 millimeters. Then we should assign this section to the blank and make sure that the definition is on middle surface. Next, we should create the material orientation. So we go to create datum and create a datum coordinate system, which the x and y axes must be equal to our global coordinate system. Okay, after the coordinate system is created, we click on assign material orientation. We choose the blank and here click on coordinate system. And make sure the normal direction is on axis 3, which is our z axis. Okay, next we should bring all the parts to assembly module and montage them in here. I don't want to change the place of our blank, which is in the origin, but our punch must rotate in this way, so the filleted edges must be towards the blank. Uh, okay, first I move the punch to here in the origin and in contact with our blank. Next, I want to move my holder. So let me see which one is my holder. Okay, this one is the holder. The holder's orientation is good, so I just translate it to, let me see, this point. This point, okay. And at last, our die must be translated to its place. Okay. Due to the thickness that we had assigned to our blank, which was equal to 1 millimeters, so the other parts cannot be exactly on the same on the same surface of our blank. So I'm going to move my parts and give them a suitable distance from the blank. First, my punch was moved half a millimeter. So here it is going to be in contact to my blank. Next, I'm going to move my holder again half a millimeter away from the blank's middle surface, and be aware that each time I choose the blank as my fixed part and the other parts as the movable parts. So next I should move my die to half a millimeter far from the mid surface of my blank. So I choose the die. Okay, I replace the die in my assembly module, so I can choose the surface easier, and then my fixed surface is the blank and half a millimeter. Okay, now I should set the distance. You can see the distances. As you can see, this distance is inputted wrongly, so I should flip. I should negitate my clearance to minus half a millimeter. Now, okay, it's done. Next, I should set the distance of my punch from the walls of the die. So first this surface, my movable surface, and this surface, my fixed surface. And here the clearance must be equal to 1 millimeter and 1.05 millimeters from both of the walls. This is from the top wall, and this one is from the side walls of the die. Assigning the arrows, and again 0.00107. This is the clearance of my mold. Okay, next we should define our solver. So we should go to step module and dynamic explicit. The time period is equal to 0.1, and I want to use mass scaling. So use the scaling definitions below and scale by factor of 200. Okay. Next, I want to make sure that STH under volume is activated, which is related to the sheet thickness in shell elements. So next, we should define our interactions. First, I want to create a interaction property. The tangential behavior is on penalty with 0.2 as the friction coefficient. Next, I want to define surface-to-surface contact between the different parts. First, the contact between the punch and the blank. So this surface of the punch is in contact with the brown side is in contact with the blank. Brown side. Okay. Sorry, I should have chosen the other surfaces of the punch too. So let me see if I can edit this interaction. I should go to interaction and right click and edit. Okay, here I can edit the region. So let me isolate my punch. Okay. As you can guess, all these regions of the surface on the punch are going to be in contact with our blank. Okay, now it's good. Okay, next, the interaction between my between the die and the blank. These surfaces of the die and the inner surfaces too. The brown side is in contact with blank, purple side. Okay. Next, the interaction between the holder and the blank must be defined. So replace the holder. Okay, the other surfaces are not needed. The purple side and the brown side of the blank. Okay, next I want to define the loads, the boundary condition and the loads. First, I want to define the holder's load. So I will add this as a concentrated force on the holder's reference point. So okay, it seems that I haven't defined reference point for my holder. So I go to part module, and here I want to add a reference point to the holder. Okay, now the concentrated force is exerted on here, and it's equal to, it's in Z direction, and equal to minus 10,000 newtons. I should define an amplitude for my step is dynamic explicit. Okay. Next, I want to define the boundary conditions of the parts. First, the die's boundary condition is going to be in caster. Die is fixed. Next, I want to assign a movement on Z direction to my punch. Here, minus 0.1. The amp is on amp 1. So my punch is moving 10 centimeters along Z direction. Next, the boundary condition of the holder. So again, on the reference point, I want to fix all the degrees of freedom except the Z movement direction, or U3. And as you know, we have modeled only a quarter of the real assembly, so I want to add symmetry boundary conditions for my blank. So choosing this edge and Y symmetric for the edge along x-axis, and the edge which is along y-axis must have x-symmetric boundary condition. Okay, next I want to mesh the models. So click on the part and start by meshing the die. First, I should seed my part. The seed global size is going to be 0.007 7 millimeters. The mesh control is element shape must be on quad, and sweep technique is used. Make sure that the element type is on explicit. Done. Next, the holder. Again, global size is going to be 5.5 millimeter. Quad and sweep technique, and again, element library on explicit. Done. Next, the punch. 5 millimeters. The global seed size. And element shape quad. Free medial axis. Okay. Explicit. Done. And at last, my blanks. Meshing. The global size is 0.003125. Okay. Due to the shape of my blank, I can use quad structured element, and the element library must be on explicit, and the family is on shell. Okay. Next, I want to create a new job. Job deep draw 1. Continue. Okay. But first, let me do some modification. One thing I forgot was that some of the parts in our simulation are moving. So for an explicit step, you should define inertia for those parts, especially when your parts are discrete, rigid, or are in shell mode. So here I will define an isotropic mass equal to 0.9 for the reference point of my punch. And I do the same for my holder, because these two components will move along the simulation, during the simulation. So again, choosing this reference point and 0.9. Okay. The inertia are created, and one more thing is that I did not create a boundary condition for my punch. Let me make sure. Okay, the last boundary condition was the symmetric. Okay. I should constrain my punch along all the axes except my z-axis. So, okay, and now the simulation is ready to be run. First, let me do a data check. Okay, the data check is completed successfully. So now I can submit my simulation. So next, you can see the results in visualization module. Okay, here is the deformed shape of our simulation. But let me show you the full deformation of the blank. So replacing the blank in here, and first I should create a new coordinate system on the edge of here, the middle of the blank. So here's the x-axis and a point on xy plane. So next we go to view, ODB display options, and on the mirror pattern tab, here we can use the mirror coordinate system. The mirror planes are going to be ZY and XZ